I apologize. My laptop is one of those laptops that needs power. I think I just broke this. Hello. Okay, so I think I have another one. Let's see. Okay, I do. Sorry. When you haste makes waste, and he who hesitates is lost. You see that? That's like a contradiction, right? Contradiction. All right. So, okay. Sorry. I should probably put my shirt back on. Okay. I'm a little hot. Okay. So, I mean, if I just forgot the power cord. Okay. So we're doing RSA, I believe. Is that what it says? Yeah. Okay. Good. Finish signatures, warnings, and term review. Okay, so there's this simple Chinese remainder theorem. If x equals a and x equals b, mod m, I'm just going to review the proof real quick, where GCD of m and n is 1. Last time I got confused and thought they need to be prime. They do not need to be prime. They just need to have a GCD of 1. They have to be relatively prime. That's what we call relatively prime. Okay? Their GCD is 1. Okay? There's a unique solution x mod mn. So what we're going to do is we're going to take this, we're going to just construct it. Now, this is the best proof. It's not maybe the most illustrative on how you come up with it, but I'm going to just do it this proof. I prefer to give proofs where you see how they develop, but this one is a math proof where we just plug and chug. Okay? So, n minus 1 mod n, there's a factor of n in it, so it's 0. Mod m, you have the n times its inverse mod m, right? So that's 1, right? Mod m. Anything times its inverse mod m is 1. Okay? And so on. This is the same idea. Okay, and then it's easy to see what to do. X is equal to a times u plus b times v. Okay? A times u is going to get you a mod m, and b times v will get you a b mod n, and they don't mess you up across because there's zeros there. Nothing happens. Okay, so again, b times v is equal to 0 mod m, so and a times u is equal to 1a. I mean, this is why math proofs are really nice. They're very easy to check. This is like machine checkable, right? It's very easy to understand and check and remember even. And the idea ex post is very nice. You're constructing these zeros and ones. We'll see that again in the polynomial interpolation. Okay? Okay, is that the only solution? Then we do the standard thing. We assume there's 2. We take their difference. X minus y is equal to 0, because if they're both solutions to this equation, then that's what it means. It means x and y have the same value mod m, and x and y have the same value mod n, so the difference is 0. But that means they're a multiple of m and n, since the GCD of m and n is 0, equal to 1. That would mean if it's a multiple of m and n, and they're different, if they're not the same, x minus m has to be bigger than m times n, which means it's not in this range. Okay? It's not between 0 and mn minus 1. Okay, that's only one solution for this. Okay, yeah. Okay, there's my poem. So now I should have done this after, right? Because this is where the 0 and the 1 were really using their properties, right? That's what we're doing. And it's deeply interesting. Even worth writing probably better poetry than that. But, so for a prime p and a not equal to 0 mod p, a to the p minus 1 is equal to 1 mod p. Again, beautiful proof, nice. You should understand it completely. You should be able to reproduce it. Okay? Consider S equals this set. So this is really just the range of the function, a times x on the domain 1 through p minus 1. And this is really a bijection, right? All different p, since a has an inverse mod p, that means it's a bijection, right? It's 1 to 1. Okay? So the set S, the domain and the range are the same. Okay, so if you now multiply all the elements of two sets that are same together, since multiplication is commutative, they should be the same. Okay, and all you have there is it's almost a triviality, right? You got an extra p minus 1 factors of a. You factor it out. You realize that this is mod p. Normally, with other things, this thing might be a problem, but you can multiply by all the inverses. Okay, and then you get that, which is a proof of Fermat's little theorem. Okay. Okay, so now we can get to decoding RSA. Okay, so we have that for RSA, when we took a message, we had the public key, which was this big N, which is P times Q, and this encoding number, right? It's just a exponent, really. It's just a number mod N. And what we do is we take M to the E. Okay? Now the decoding is you get some message. Maybe I should have called it X or Y because it's not the message anymore, but it's a message you received, and then you raise it to the Dth power mod N. Okay? Fairly simple. Okay. And N is the product of two primes, and D has this property. D and E have this relationship. D is a multiplicative inverse of E mod P minus 1 times Q minus 1. Okay? Nice. Very nice. Okay. So M to the, what we would like is a message that goes in, M to the E, and then that's the message that goes across the wire, the thing inside the parentheses, and then the decoder gets it, and then raises it to the D. And so what should happen when you do this is M to the E D, right? You multiply exponents when you raise it this way, is it should equal M. Okay? So that's what we need to prove. Okay? This is what we need to prove. That M to the ED is equal to M mod N. And now already you see, well, look, there's some P minus Q's and P minus 1s and Q minus 1s in the exponent. And N is mod P and Q. So you know that P, something raised to the P minus 1 mod P is 1. Right? So you have some nice properties to work with, right, already. We built up some structure. Okay? Okay, another view is D equals, instead of saying, we're just changing this thing to an equation, right? We say D is the inverse of E mod P minus 1, Q minus 1, and we do this a lot, okay? And we say E, here we're saying that means, what does that mean? E times D is equal to K times P minus 1, Q minus 1, plus 1 for some integer K. Okay, these days I dropped the for some integer K on the slides. Okay, that's just what it means to be an inverse, right? E times D is 1, so that means that E times D equals 1 mod P minus 1, Q minus 1. It means it's E times D is equal to 1 plus some multiple of the modulus. Yeah.
Wait, from M to the power of B, then M to the power of B, how did you, don't we know that E is 1 only in mod P minus 1? How are we able to make it into M in mod N?
Yeah, that's what we're trying to do. We're trying to prove that statement. Yeah. That's what we want. It says we want that. We don't always get what we want. There's a song. Have you heard of that song? You don't always get but sometimes you get what you need. No? Nobody? Okay. That's what we want. Okay, I should have put that in red. We don't know it yet, right? Okay, but this time we will get what we want. Okay, so, okay. Okay, so I'm getting the endorphins from trying to run up the hill, I guess. But, okay. So Fermat's little theorem says this. So it's sort of related. This isn't going to work, but you can kind of see there's a pattern here. Well, there's a P minus 1 and Q minus 1. We have this thing where if you take something to the exponent of P minus 1, it's cool, right? If you take it to some power of the exponent, it's cool, right? It equals 1. A to the P minus 1. Now you take that whole thing to the K. 1 to the K is 1. Nice, right? And that says A to the K times P minus 1 plus 1. Now we're getting there. We're almost like the ED. Okay? And that equals A mod P. Okay, except it's not right because there's something missing, right? The Q minus 1 is not here, so what? And the P is not P times Q, right? Okay, so well, that's what we really want. Okay, so but it looks kind of similar, right? Okay. Okay. So now what we're going to do is we know how to work with mod P And we know how to work with mod q, right? We have this nice Fermat's theorem with it, right? Yes. No, he's asking where this k came from. Where did k come from? Yeah, you tell me. You tell me. Okay, we started here at the AP minus 1 to the 1. Now if we raise both sides of this to the k. Yeah, okay, sorry. It's just better to learn if you tell me. It's better educational experience for you, okay? So fear is not so great for education, but confusing is fine. Confusion is the sweat of learning, so it's fine. So, and the best way to get unconfused is to convince yourself, right? That you own the process, okay? Okay, so E is D minus 1 Q. This is another way of saying it. What we're trying to do is understand x to the ED. I changed it to x. Okay, so, and I'm using this Fermat's theorem saying now I could write this x. I could just write it as whatever it is mod P and whatever it is mod Q. There's only one way to write it that way. You just take it, right? So now x is equal to this, right? So I'm just using the CRT theorem, okay? So x is equal to A mod P and x is equal to B mod Q. So now let's just plug in, right? So let's just plug in A, work with it mod P, and see what happens. Well, now I can do what I did the previous slide. That's why it was really important for me to go over that step that was missing for this gentleman. Because it's the same sort of thing. I'm taking this whole exponent here and trying to understand it. Okay, so the 1 gives you the factor of the A out front. Then there's an A to the P minus 1. That's the thing inside the parentheses. And then I take it all to the K times Q minus 1. Okay? I probably should have done this in a couple of steps. But again, if you own it, it'll be easy for you. Doing that work yourself is better. Okay? And so then, what do we have about this? Now I claim this is A. Where do I get that? Well, I know this A to the P minus 1 inside the parentheses. What is that mod P? 0 and 1, which is I love 1, right? 1 we love, okay? Because now we get the 1 in the middle, and then it's 1 to the power is 1. 1 times something is that something, right? Okay, excellent. So that's by Fermat. This is by Fermat's theorem, that A to the P minus 1 is equal to 1. Okay? And this is exactly the same. Right? Nice. So now we have x to the ED in this weird other system, this PQ system. We have x to the ED is equal to A, and x to the ED is equal to B. Oh, look, that's what it looked like before, right? X was equal to A, and x is equal to B. We know only one thing corresponds to that AB, and it's x. Okay? And that's the proof. Okay, does that make sense? CRT plus FLT. And then you get the proof. Okay. Nice. Questions? Okay. Okay, so now, okay, so what we've done is, I should have reviewed. Okay, so now I've shown you a way to encode messages and decode messages. And, right? And what we needed for that is we needed some primes. We need to know how to do exponentiation. We need to know how to do inverses, right? Yeah. Oh, B equals 0, yeah. Or B equals 0. Yep. He's saying that, yeah, if you didn't see it, it's fine. It's just the same thing as before, but it's B equals 0. Okay, so find large. So what do we have to do to build the system? We have to find large primes, P and Q. Okay? So are there large primes? That's the first question. Right? Maybe there's no large primes, or there's not very many, or maybe they're hard to prime. Maybe they're exponentially unlikely to be there. Right? Maybe when you just pick random numbers, they're not prime, usually. Right? And so this theorem says the number of primes less than n is about this many. Big N over ln n. And then now this is the value n. That's why I'm using the big N here. Okay? Choosing randomly gives approximately 1 in ln n chance of the number being prime. Okay, so once you pick random numbers after a point, you're pretty sure you have one of them that's prime. But the next thing you need to do is be able to tell which one is prime. You shouldn't use numbers that aren't prime. Okay? So that's not going to happen in this class. You add 100 and you can go to 170, and then you can learn how to do this. It's called the Miller-Rabin test. It's very nice. It's not so bad. It sort of uses an approximate converse to Fermat's theorem. Our evil TAs may stick it in the discussion or homework for you. He's grinning. Okay, so and in fact nowadays, recently, probably about 5-7 years ago, they proved that there is a polynomial time algorithm, even not randomized, that tells you whether something is prime. Okay, so what this says is for this sort of length number, 1 in 700 is prime, just for the parameters that we work with RSA. And so it says, yeah, you can do all this, right? It's not so big. A computer can sample 700 100-digit numbers and do a quick algorithm on it. Okay. So now you need to choose an E with a GCD of E and of this thing being 1. We know how to compute GCDs. We can find the inverse of E, which is D, using the extended GCD algorithm. So all steps are polynomial and log of the value of the number, or polynomial in the number of bits. Okay? This is why we went through this process of doing repeated squaring, and I guess repeated squaring was extended GCD. All of those are used all the time. Okay? Okay, so now let's prove security. Okay, wait. Who thinks we're going to prove security? Okay. No, we're not. We're not going to prove security. Okay. I don't know whether it's secure. That's the truth. Okay. So the truth, whether you're ready to take it or not, I don't know. So Bob, this is the idea of the security. You see that parentheses? Bob doesn't know what's inside the parentheses. He knows N, but he doesn't know P or Q. Alice knows P or Q. So you can't, so in some sense, he knows P and Q because information-wise, what P and Q are is in N, right? He can tell, if I tell him P and Q, he could easily multiply them together and see if it's N. But the issue is, he doesn't know D either, but he doesn't know the factorization of N. Let's just focus on that. And that's what he doesn't know. And it's not clear why that's secure. Okay? It's some sort of assumption that we just don't know how to factor. That is the actual total security of it. Okay? So there's no proof there. It's I don't know is a proof. Okay? Yeah. I don't know how to break the scheme without factoring in. No one I know or anybody I've heard of admits to knowing how to factor in. I mean, maybe the Russians know, maybe the Chinese know, maybe the NSA know. I don't know, right? They may know, and they're reading all your messages. That's fine. So, but I don't know. I taught a class at Princeton. There's somebody who got, like, on the final a 90 blah, and the next highest score was a 60 blah. And that next highest person is a famous professor here at Berkeley. So that guy who got the 90 blah works for the NSA. So maybe they know. Yeah. Maybe they know. I don't know. Yeah. There's another guy I know who worked at the NSA. What he could do is he could take a Rubik's Cube. He looked at it. Now, he wasn't very coordinated. So he could never compete on this speed Rubik's Cube thing. So what he could do, and this was a long time ago where it was sort of more new, he could look at it, and then he'd put it behind his back and solve it without looking at it again. Yeah, he works for the NSA. So, yeah. Okay, so if Bob sends a message, a credit card number to Alice, do you see and he codes it using Amazon's Alice's public key. What could Eve do? Eve gets to see everything. We're in the public internet. We're in a wireless here. Okay? She sees it. What could Eve do? She could send the credit card number again. Yes. I could buy toilet paper. Okay, so the protocols are built on RSA. The real protocols are built on RSA. RSA is a tool, but you have to do much more, okay, to make it work. For example, there's several rounds of challenge and response between your computer and Amazon when they're setting up the schedule, the system. And in fact, the eventual system doesn't even use RSA because RSA is too expensive. First, you trade a secret key, and then you use that secret key to actually do your most of your communication because it's just too expensive to do even these operations. Okay. One trick is Bob. How does he get rid of this? Bob encodes the credit card number and a random k-bit number R. Okay. And then that makes it so he never sends just his credit card. He can send his credit card and a random k-bit number R. And now he also tells this k-mint number maybe something they agree on, Amazon and him privately. And so then Amazon sees it, and just knowing it's a random k-bit number R makes this message completely random looking. If you send it again and you use a different random number R, then Amazon's going to be mad at you, and they're going to say, I believe you're Eve and not Bob. Okay? That's an example. So there's a lot of these tricks to do these things. Yeah. Just put next to each other. So what you think of is you're encoding 100-digit numbers. So the credit card is a 10-digit number, and then you could add a random number, which is 90 digits. Just pick one. And then when you encode that message doesn't look like any credit card number. Like Alice can't send that one again because she'll see the R there. Okay? So when you've already established a connection, so that you can, what could happen in fact is Amazon could tell you to encode it with this random number. Okay? And then if you send it back, the next time Amazon's going to give the new person a different number, and then it will, but there's lots of these arguments you have to do. And there's CS9. Okay, so now the next thing is these signatures, right? So there's this notion of signatures, and so let's try to cover up my gut here. You don't have to see that. Okay, signatures are another thing you can do with RSA. Okay, so and that is inside out. Yeah. Okay, so now, so what is, here's another thing you may want to do. Like, how do you know Amazon's public key? How do you know it? I don't know it, but I want it, right? I want Amazon's public key. Okay? So what I have is my browser knows VeriSign or these other public keys. It knows a few public keys. I just know one public key, say VeriSign. And Amazon says, oh, okay, both Amazon and the browser knows this VeriSign's public key. I just need to know one. But I'm going to talk to many, many different commercial sites, and I want to find out all their public keys. So before they're even allowed to have a public key, they have to go to VeriSign and say, hey, I need this public key signed. Can you sign and say this is my official public key? And then when the browser goes to that place, Amazon will say this is my public key. Now, should you believe Amazon? How do you know you're talking to Amazon? How do you not know you're talking to some kid who's hijacking the wireless in this hall? Give me your public key. The kid gives you a public key. It's not Amazon's. It looks like Amazon's, but it's not Amazon's. How do you tell whether it's Amazon's public key? Okay, so you can't. But what you can tell is your browser already has at least one public key, VeriSign. Okay? And what Amazon has done with this public key is, again, VeriSign has the public key. Everybody knows it. You know it, and Amazon knows it. The whole world, your phones all know it. Okay? And now what happens is the thing you want from Amazon, hey, give me your public key, right? You don't want to have to go look it up somewhere. Just give me your public key. Okay? So Amazon gives you their public key. I am Amazon. My public key is case of Amazon. Okay? Now, what VeriSign does, in addition to that, this is a message. right? You can just think of it as a message, some 100-digit number, right? We can translate it to a 100-digit number. Okay? I am Amazon, my public key is whatever. Okay? So now VeriSign, what VeriSign will do, will sign it. They'll sign it. They'll do something called a signature of this public key, which is weird. It's going to decrypt this public key, this message, not this public key. It'll decrypt C. It's using the RSA decryption function, C to the D. Does that make sense? Weird, right? And then, okay, so then what Amazon does is it has this message inside the C. Remember, it says, I'm Amazon, here's my public key, believe me. And it also adds something else. It says, here's a signed copy of this message from VeriSign. And you know VeriSign's public key. Okay? So now, what do you get? You got C. You got the signed copy of C. What should you do? You should verify that VeriSign signed it. Okay? That's a valid signature. How do you know that S of V of C is a valid signature that says VeriSign saw this, they agree with this message, they're putting their signature on this message. Okay? So what the browser receives is C and some Y. It doesn't know what the Y is, but it knows what it should be. It should be a signed copy of C. Okay? Where the signing for the signing is C to the D. It's just taken C to the D mod N. It knows D and N because those are VeriSign's public key. Okay? So what it does is, what if it just tries running the encryption algorithm on Y? Weird. Okay? So let's do it. Okay, so I have the signed copy of C. Okay? I take that signed copy of C and I raise it to the ETH power. Now what should this signed copy of C be if it's all valid? It should be C to the D. So I could plug in C to the D. Oh my. What is C to the DE? Right? Is that like, right? I can verify it. I get back C. I got this message here. I got C. I got some Y. It's some weird old bunch of bits. I take it to the ETH power. I get C. So that says this message, I am Amazon, my public key is KA, was signed by somebody who knew D. That's our assumption. Okay? So, otherwise if you don't know C to D, right, there's only a few things you can put up here to make it undo, right? Okay, that's all in the security part. Okay? Okay, so it says, oh yeah, I am talking to VeriSign, yeah.
Wouldn't this mean that more or less the entire internet is secured by the assumption that nobody other than VeriSign knows VeriSign key?
Yeah. Okay, so you can see this. Let's see, where is this? Okay, you can see this in your browser, right? There's DigiNotar, right? They have their server, they have these authorities, right? It's in my browser, right? So if my browser is messed up, okay, and there's these authorities, right? You could look at them. It's kind of fun, I guess. Blah, 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 details. So look a bunch of blah, blah, blahs, and then some more blah, blah, blah. So it's a version this. There's an algorithm, RSA, right? So I wasn't lying. Okay, so, and you could also see that somehow, I don't completely understand this, so it's a little dangerous. But there's also all these commercial products, including Amazon is here somewhere, I believe. And we can take a look at that if you want, but whatever, okay? Okay, so now let's address the student's question. It kind of relies on these messages being okay, right? So public key cryptography is this, the signature scheme is this, right? The same mathematics give you both. They give you a way to verify identity. Only the person who knows how to write that signature can write the signature, and so on. Okay. Yeah, okay. Well, you can also get once somebody got one of these DigiNotar to certify fake certificates for Microsoft. And that you might not think that's bad because who goes to Microsoft? Unless you're unfortunate enough to use Windows, and then all your updates are from Microsoft using the certificate assigning. And I think you should just throw the computer out anyway or reinstall, but okay. You still don't want that, right? In 2001, they signed they signed a certificate that was just not for Microsoft. Somebody called them up and said, "Hey, can you get this signed for me?" And somebody said, "Sure, just pay me." And there they went, right? So it's a little bad. And it happened again. Maybe it's due in 21. Did you know, Tar, that's a certificate of authority I was showing you. That is the person who did it, right? It's still in my browser. Okay, not that Microsoft one, not the broken one, but that's a certificate of authority. So now there's this a human engineering aspect of hacking, right? This is what people are doing. Yeah, and the question is, it's also a chicken or an egg. How do you? You want them to actually sign certificates for you. So you have to set up the process where Microsoft can verify their identity outside of this whole system to get started, right? Otherwise, it doesn't make sense. Okay, so public key cryptography, it's the RSA scheme. That's the whole scheme, not too big, not too nasty. I think that's, it's the whole description. And from all of these, you know how to do all the parts. You know how to multiply. You know how to take inverses. You know how to exponentiate using repeated squaring. Fermat's theorem and the CRT gives you correctness. It's good for encryption and secure signature schemes. Okay. Questions? Yeah. No, you generate a public key. I don't know. Yeah. I mean, generally, so you can go to GoDaddy and start your own website that's secure, and you can go through the process. So what happens is you just upload a public key. They're not checking it against anything. They just somehow, your account information, the fact that you have a login, gives you the authority to generate a public key for that that's signed by them.
Yeah, but how do the signing authority, let's say I'm requesting Amazon, and somehow I get like a public key that wasn't Amazon?
No, you understand that Amazon generates their public key every time they ask for it to be signed. So it's not like there's nothing public out there. The public verification of what's out there, when you make you're always, when you're asking them to sign something, essentially asking them to sign a new thing. So there's no place for them to look up. It has to be through our normal societal channels that they verify the identity. Right? I mean, it's outside of the system. Yeah. Okay. So, midterm review is okay. Let's go over the semester, I guess. Do you want to take a break first, or you want a break? Okay, let's go. Okay. Hey.
You know when I can find you today and have you sign the time sheets?
Yeah, I can do it right after if you want. You have them, or?
Yeah.
Okay. I can do them now, actually, if I can find the... Sure. Okay, so let's go through the semester here. Statements is that a statement? Yes. Okay, is that a statement? Okay, is that a statement? No, because it's not. It has to have a value of true or false. Is that a statement? Is that a statement? Not a statement. It's a predicate. Okay, what's a predicate? Is that a predicate? Yeah. Okay. Given a value for x, it becomes a statement. That's what a predicate is. Is that a predicate? Yes. Is that a predicate? Yeah, it's a predicate on two free variables, x and y. Is that a predicate? I mean, maybe if you decide it's true, false, and plus means and or something, but not with arithmetic. It's an expression, not a Boolean predicate. You can have an expression that's a statement, but then it has to evaluate to true or false. There's quantifiers for all x, p of x. For every x, p of x is true. If there exists an x, there exists an x where p of x is true. Okay? For all n in the natural numbers, n squared is greater than or equal to n. Okay? That's the way you can use it. It's phrasing English sentence that says that the square of a number is larger than the number. Okay? And you can formulate it this way. Here it says, for all x, there exists in the real numbers, there exists a y in the real numbers that's larger than x, meaning there's no biggest number in the reals. Okay? Okay, so connecting statements, you know this, right? Or, and, not, those are fairly straightforward. Proposition, expressions and logical equivalence, A implies B is the equivalent to this, not A or B. Okay? You should understand the notion of logical equivalence. You should understand in particular what implication means. You should understand in particular what that implication is actually equivalent to this logical statements with negation and or. Okay? And this is De Morgan's law. If you take a negation of A or B, you get not A and not B. Right? And you could even argue, you should be able to quickly argue to yourself it's true and not just remember it. Right? It's, to me, I don't remember these things. I just sort of remember how one argues about them. Okay? So, I mean, maybe this one I remember, but even this one, when I looked at it, I was like, how do you argue that? Right? So you should be able to make these kind of arguments quickly. Okay, proofs. Truth table or manipulation of known formulas, right? You could either, you can prove the equivalence, logical equivalence, using a truth table approach. Just sort of fill out the truth table and make sure that they have the same values, output values for all the combinations of the input values. That's what a truth table is. It's just a table telling you check every value. Another way to prove it is just sort of put together what you've already proven. Okay, so this is one of them. It says for all x, p of x and q of x. Means it's true that this statement is true for all x, p of x and for all x, q of x. Okay? Does that make sense? And you could try to make yourself a little argument here. If for all x, both of these statements are true, it must be true that for all x, the first statement is true, and for all x, the second statement is true. Okay? Okay, so, and then proofs. A is even implies that A squared is even. Basic trick in proofs is you understand your domain. The domain here is numbers. With numbers, the way we reason and argue about them is using equalities, right? So what you do is you take the statement from this English statement to one of equality. Like, what does even mean? Okay, it means it's a multiple of 2. What does it mean for a multiple of 2? It means you get this equality, A equals 2K. Okay? So now let's plug that in. We could start with this equality and try to work with it and see what happens with A squared. How do we turn this inequality into A squared? A equals 2K. Well, E square both sides. Okay? What is even? Now we go back. We use the definition of even again, and we factor out a 2, and we see that A squared is 2 times some integer. Okay? And so on. A squared is even. So the contraposition, P equals proof by contraposition, is you could either prove either of these statements. P implies Q or not Q implies not P. That's the contrapositive. both of those are the same statement logically. They're logically equivalent. A squared is odd implies that A is odd. The contrapositive is A is even, implies A squared is even. So now all we need, instead of proving that A squared is odd implies A is odd, we need to prove this. Oh, look, we already did. Okay, so we're done with that one, right? Does that make sense? The direct proof was very easy in the first case. In the second case, I don't know how to do a direct proof, but the contrapositive is in fact really quite easy because we just did it. Okay? Okay, so not P implies false. So you start with not P, and usually the way these things develop is we use not P, then we make some statement in the middle which follows from not P or follows from other facts, and then we make some other statement in the middle which is not R, and then if you see a statement and its opposite, you know that together those are false. Okay? So it's very useful for proving something does not exist. It's going to be the rational representation of root 2. And there too, we started with the assumption of falseness and said there is a representation, and then that made it concrete. To say there's no representation, A over B, it's hard to reason about that. So what you do is you assume there is a representation. Then you can start using formulas and inequalities, and then you get these contradictions. Okay? So, okay. A finite set of primes, there too, it was one that says that there's always more. How do you always show there's more? In this one, the nice proof would have been, nice proof to say there's an infinite set of primes. A finite set of primes does not exist. So we assumed something that had some structure. We started working with those things, and then we showed some ridiculous stuff. And so therefore we knew that set did not exist. We had something concrete to start our proof with. Okay. Row couple does not exist, right? So we do that too, and then we, is that a contradiction? Yeah. I don't know what proof I was talking about. Okay, so in there's all kinds of... Stable marriage is great for proofs. It just has really nice proofs. I'm not sure whether I'm talking about the optimality proof or what. Okay, so right, yeah, we that's sort of the contradiction in a lot of the stable marriage proofs, right? We say, if this happens, the row couple must have existed, and therefore this didn't happen. Okay. Okay, so now we're going to go forward and see contradiction and induction. I wanted to talk about this here because this is the well-ordering principle and stable marriage, right? The first day where a woman does not approve. The first day where any man is rejected by the optimal women. So we use that. These are statements that will eventually be false. There is no day where the women do not approve, right? So what we do is we assume there is a day the women do not approve. And not only do we do that, we then use the fact that there's a first day that women do not approve. And then we use all of that structure to build our argument. Okay? And we did this here, the first day where any man is rejected by his optimal woman. We started this proof of male optimality using that notion. We're going to assume for the sake of contradiction, if it's male optimal, they're not rejected by their optimal women. Nobody is. Okay? So therefore, let's assume it's not male optimal for the sake of contradiction. Okay? And now, the extra thing we do on that is we add the notion of first time when somebody was rejected. And then we use that extra fact or that extra condition to actually in our argument. And it helped us. Okay? Okay, so they do not exist, right? So neither of these things happen. They don't really exist in stable marriage. So we assume they exist, and then we prove that, that's a contradiction, so they must not exist. Okay. Okay, and then we went to induction, and this is this notion that if you prove P0, and for all n, you can go to the next spot on the ladder. That's equivalent to having proved this statement, this for all statement on the right hand side. That for all n in the natural numbers, P of n holds is true. Okay, so Here's an example, induction on n. So the base case is 8 divides 3 squared minus 1. The induction hypothesis is we assume P of n, that's true, right? 8 does divide 3 squared minus 1, right? Is that what it says? Yeah, because 3 squared minus 1 is 8. 8 divides 8. Okay, so the base case is there. So now we want to prove P of n plus 1. So we start with the statement, right, that we're trying to prove. In this case, this is how I'm organizing my proof. Is that I'm saying I'm just plugging in n plus 1 into this theorem statement. Okay, or the right-hand side there, the 3 to the 2n minus 1. Where that n is, I put in n plus 1, so I get this 3 to the 2 times n plus 1, which results in this 3 to the 2n plus 2. Okay? So now I factor out a 9 for some reason, because why not? And that because now I see that now I can almost see my induction hypothesis, right? That induction hypothesis is that this 3 to the 2n minus 1 is equal to 8 times d. But I'm clever. I can put the minus 1 over there and make a 8d plus 1. 3 to the 2n is 8d plus 1, right? Okay, so that's what I'll do. Okay, and so on. And now you reorganize. You're trying to get this to be a multiple of 8. And you can see that it is now, right? You multiply through by 9, you get a 9 minus 1 out there, and yeah, okay. So you get that. So now this thing is a multiple of 8. Okay? And now, again, I'm using equality here. This divide symbol is nice for English. It's really sort of an English symbol, but then I said I use the notion that it's divisible by 8 because 9d plus 1 is an integer. You got to go look at what d is, but it's an integer. Okay? Okay, so, and men and women, each person has, this is the whole, quick review of a stable marriage. I talked to the TAs, and they said one summer they didn't do a stable marriage at this time. And he was like talking about how great it was because, it was much better, went much more smoothly. It's like, and we discussed it. And I said, it confuses the students. That's true. But I think it's important for various reasons to name things. I mean, one of the tricks you do a lot here is you see this MIWJ. We're sort of writing down the names. We're saying there's a boy B, and then we argue about the B, and we have to be precise. It's a way to get you from the notion of formula, which we had just done, where we have the sequence of equalities, where you translate in inequalities and then you use your arithmetic reasoning. Now we're going to ask you to understand how to reason about other objects. So you need to build up theories around those objects and work with them. And that's what we're doing with the men and women. And in there, too, it's convenient. There, the process is this naming of there's a boy, the first boy who did this, and then there's another boy, and then that's B prime. Look at these things. Now we can really understand which is which and what they're doing and state properties about them. Okay? That's the good thing. But the TA was correct. The bad thing is it confuses you. And I said, this is the confusion is the sweat of learning. I think that's a feature, not a bug. So it gets you. It's okay to be confused if that's just the process. Okay. Anyway, how many pairs? There's n pairs in the pairing, so that's what a pairing is. People in pair are partners in the pairing. That's what we just call them. A row couple in a pairing they're not partners. They wish they were partners. Okay, that's what a row couple is. Okay, if you have an entire pairing, you have some MJ and WK. Here's where I sort of am using my symbols to add some, MJ and WK who like each other more than their partners. I'm using the definition partners here. Okay? The stable pairing is a pairing with no row couples. Does a stable pairing exist? We showed you that no for this roommates problem. We showed you this example with the stinky roommate that nobody wanted to be with. And that, along with the cycle among the other three, made it rotate a lot. And in fact, that's sort of a fundamental example in economics that says you can't get certain conditions. You can't make everybody happy because of these kind of cycles and preferences. Okay, so this all came from economics, the study of rationality and economics. So it's actually a very cute idea. It's fundamental. to economic theory. It's called the Eros theory, or these sorts of things. I mean, there's a lot of these theorems. Arrow got a Nobel Prize for his work on this kind of there's no rational system for all preferences with the roommates problem. Okay, but with the stable marriage, there was this algorithm that not only can you prove that there is a stable pairing always, it gives you a method by which to construct it. Okay, and here's the thing. We all remember the video of those TAs whining about how hard it was to be boys. I don't know. I'm just saying stuff. Okay, so all men propose their favorite non-rejecting woman. Every woman rejects all but the best men who propose. Right? Okay, so now we've set up our definitions again. Right? The man crosses off a woman who rejected him. The woman's current proposer is on string. And either men propose or women propose. That's what, when we say propose and reject, that may be what we mean. Okay? Okay. So traditional is a propose and reject where men propose. And the key property here is the improvement lemma. The person who's getting proposed to quite clearly just can only get better because they still have the previous person on the string. That's the idea of the improvement lemma. Okay? If man is on the string for a woman, any future man on the string is better because you have the previous man there. Okay? No rogue couple. You see, the proof of that is that assume there's a rogue couple, MW. M proposed to W. W ended up with someone she liked better than M. Right? That's because of the improvement lemma. Right? So the rogue couple means that why did the man M propose to W? It's a rogue couple because the man likes W more than he likes his partner. So if man likes W more than he likes his partner, the man must have proposed to W first and been rejected because he goes in order. Okay, that's the algorithm. Okay, and then that says the man must have proposed to W, so she must have rejected him if he didn't end up with them. Right, the rogue couple is not a pair in the pairing. Okay, so she rejected him. If she rejected him, that means she saw him at some point. But so whoever she ended up with by the improvement lemma is better than him. Okay, so that's the proof, not a rogue couple. Okay, so here we're assuming for the sake of contradiction there is a rogue couple, and then we show there's not a rogue couple. That's ridiculous, right? Okay, so meaning the contradiction here is we're assuming M and W liked each other better. Here we use the fact that man likes W more. Here we're saying, oh no, W likes her partner more than M. So that's not actually a rogue couple. So those two statements are not true. So here, even the simple act of naming the M and W just gives me this infrastructure to go look at it and say, I understand what's going on. Right? And make the arguments precise. Okay? Okay, so the optimal partner, it's getting my intuition into a form I can make a clean argument. Okay, so optimal partner, if best partner in any stable pairing, it's not necessarily the first in the list. That's not what it means. We're going to ask this question in the midterm. It's maybe we'll ask it. I don't know. Something's on the midterm. But optimal partner doesn't mean the first on your list, right? It means because there may not be a stable pairing with where you are paired with this partner. It's my Nicole Kidman example, right? If you remember that. It's there's no okay. It's just it has to be a world where that your optimal partner is the best partner you can get in any stable pairing. It's conditioned on that. Okay, so the man optimal pairing is a pairing where every man gets his optimal partner, and the TMA says the male produces the male optimal pairing S. Okay, so this is where we use a well-ordering principle. First man M to lose his optimal partner. So there's a better partner W for M. Okay. Okay. So in T, he's paired with W. different stable pairing, right? So he asked, we're just picking the first man M to lose his optimal partner. So that means that he has an optimal partner. Let's just call that W, which is better than M. And that they're partners in this different stable pairing. There must be another stable pairing where they're partners. Now, if he liked W better, he must have asked her, right? But there's some M prime who bumps M off in the table. The reason he didn't stay with her is because she rejected him, right? Okay, and if she rejected him, there must be somebody else who she liked better, M prime. Okay? Now, W prefers M prime, right? So W prefers M prime to M because she chose M prime over M. M prime likes W at least as much as his optimal partner. Why? Because he hasn't been rejected by his optimal partner yet. So he's never been rejected. If he's reached W, right, in his list, he hasn't been rejected by his optimal partner. So he likes W at least as much as his optimal partner. W may be his optimal partner. W may reject him later. But at this point, he likes W at least as much as optimal. And that's where we're using the well-ordering principle. We're using the fact that M is the first guy who got rejected, not M prime. Right? So it's very useful to have this well-ordering principle here. Okay. Since M prime was not the first one to be bumped. M and W prime, M prime and W is a rogue couple in T, right? They like each other more than M prime likes W more than his, quote, optimal partner, or at least as much as an optimal partner, which means in T, he likes M prime at least as much as whoever he's paired with in T, right? There's this argument, this short but subtle, that you really need to understand what all the symbols mean. Okay? And so, the theorem is women is pessimal. Man optimal means if it's good for men, it's bad for women in this case, unfortunately. And vice versa. Okay, so questions? Yeah. You need to name all your symbols so I can understand. Sorry, it was a joke. Okay, he's asking what happened here? Okay, so where's the well-ordering principle? Where's the power in the well-ordering principle? There's power. This is power. Okay, so let me show you the power. Okay, so M is the first guy to get bumped, right? Now, where am I using this power? I'm saying M prime likes W at least as much as his optimal partner. That's where I'm using the power. Because I know that he's asking W. Okay? If he's asking W, he didn't already ask his optimal partner. Why? Because he wasn't bumped by his optimal partner yet. Right? Because he's not the first guy to be bumped. Right? There's a different guy who's the first guy. So he has not been rejected by the woman of his stable dreams, right? Yet. He's asking this W first, right? So it says this W is at least as good as anybody could be matched in any stable pairing, which is what I'm saying here. The M prime likes W more than anybody he likes in here, in this stable world. Okay? Yeah. Okay, so I'm very much, there's two lines there. This M prime likes W at least as much as an optimal partner. I am using the the well-ordering principle. That's where I'm using it. Okay, so, G equals V is a graph with vertices and edges. V is the vertices and E is the edges. Its pairs of vertices. There could be ordered. These are terms you should know. Adjacent means two vertices that have an edge between them. Incident means an edge is a term I use to talk about the relationship between edges and vertices. And degree is the number of edges that are incident to a vertex. You can do all this with directed graphs. Sum of degrees is 2 times e. Some people, it's actually maybe nicer this way. I like this theorem. You've seen it a lot of times, this lemma. But one way to think of it is this handshake lemma. It's sometimes called the handshake lemma, where you say an edge is a handshake between two vertices. Okay? And then you just count the number of people who participate in handshakes. Okay? So I can count it from my point of view, is how many handshakes did I make? Right? That's my degree. Okay? Another point of view is for each handshake, 2 people participate. So the total sum of the number of handshakes of all the people that all made, that's the sum of the degrees, is equal 2 times the number of handshakes. Okay? And just replace the word handshake with edge, and it's the same thing. Okay? Degree of vertices of total, you just count it 2 ways. Pair of vertices are connected if there's a path between them. Connected component is a maximal set of connected vertices. Okay? It's sort of the maximal thing. Okay, so a connected graph is one connected component. Okay, every connected graph where every vertex has an even degree has an Eulerian tour, a tour which visits every edge exactly once. You take a walk using each edge at most once. Now taking the walk, then we started thinking a little bit. It's about you return to the starting point. You can always return to the starting point. Now you're thinking about graphs and parity, right? It's a parity argument. Right? Because since the degree is even, whenever you go to a node, you can always leave. That's our idea. So eventually you have to end up back where you started to get stuck. Okay? For any intermediate node, you could always leave. The starting node, well, you come back to it and you get stuck. Then you recurse on the connected components and you put it together. The walk visits every component because the original thing was connected, and so on. Right? So there's always arguments. Every single time I say one of these things, like I'm thinking, why is this true? Okay, and then I either tell you or I don't, or but you make a choice how to understand it. When you're doing that, when you read the material, you should do the same thing. You should read a statement. You should be able to go one level down and say, why is this true? And maybe one level down and go, why is this true? Okay, until you're completely convinced, and go back and forth in that process. Okay, how many faces in a planar drawing of a tree? This is Euler's formula. How many faces in a planar drawing of a tree? Okay, yay, you can read. Okay, so, but you can also think, right? So now, maybe I should have drawn you pictures, but draw your own in your head. That's even better, okay? You draw a tree, there's one face, one connected region of the plane, no cycles, right? Okay, how many edges? V minus 1, right? This is the definition of a tree or in many different ways. Okay, Euler's formula is V plus F equals E plus 2. And that's the base case. We have that, right? V plus 1 is equal to V minus 1 plus 2. So we have a base case for Euler's formula. And then the induction step is adding an edge splits one face into 2. So that just says you add 1 to the number of edges and you add 1 to the number of faces and the equality still holds. So even here, we try to work with it. This is a formula, so we're going to prove it using this equality and try to work with this formula. Okay. So a coloring of it. So given G equals VE, a coloring of G assigns. Okay, yeah, you should know this, right? Is that a coloring? No, that's not a coloring. You've seen this picture before. That's not a coloring. Okay, so the first two are not so interesting. You just colored every vertex different colors. But the last one's really quite interesting. You're only using 3 colors, and there's a lot of vertices, and there's even a high degree node. So there's something you can maybe do here in terms of algorithms. Now the dirty truth is there's not so much we can do beyond this, but for planar graphs we can do stuff. Okay? Interesting so this is the idea. It says that this is some world. You see how I've colored in the colors of the country, so everybody, you can tell them all apart, right? And that says any long border, any non-point border there should be different colors for the two countries on different sides of that border. Okay? And you can model that with a planar graph. This is the way I'm doing it. I'm just drawing a node for each country and drawing connections to adjacent countries or adjacent states or whatever it is. Okay, so this four color theorem is really a color. It's usually stated as you can color a map with four colors. It's actually the same statement as you can color a planar graph with four colors. Every planar graph can be colored with 6 colors. We used this formula. We said that there's not, in some sense, intuitively, there shouldn't be too many edges in a graph. If it's going to be planar, we can actually sort of use that we can take that intuition and carry out this proof that says, in fact, that's true. There can only be this many edges in any planar graph. Okay, it doesn't mean that any graph with this many edges is planar. It just says it's a necessary but not sufficient condition. Okay, from Euler's formula. Okay, so that's from Euler's formula. We argued about faces and face edge adjacencies, and then we derived an inequality with that related faces to edges, and then we eliminated the face variable, right, and the inequality. Okay, so again, we use the tools at hand. Inequalities with too many variables, you got to eliminate the variables. How do you eliminate the variables? Here was an argument about face edge adjacencies to derive another inequality. And then from that inequality, we can put them together. Okay? So the total degree is 2e. The average degree is divided by v. It says that there's some vertex with degree less than 6, or at most 5, because there are integers. Or they're even natural numbers. Remove the vertex v of degree 5. Inductively or recursively color the remaining graph. Color is available for v since there's only 5 neighbors. Right? There's 6 colors. Your 5 neighbors have used up 5 of them. You must have one available for you. It's the pigeonhole. It's something like the pigeonhole principle. Okay, so only 5 colors are used. Okay, so that's the 6-color theorem, which isn't far. We're like only 50% off from the 4-color theorem. We can get a little closer to the 5-color theorem and connected components. The key idea in the 5-color theorem is this lemma that I argued in class, is that if you it's similar to the map theorem, right? It says if you have a map with red and blue, you can switch to red and blue. Now, if you take the subgraph say you have a coloring of your graph, and you take 2 of the colors, any 2 colors, and you take the subgraph induced on those vertices. Okay? Now you look at the connected components in that subgraph, you can switch the colors in each connected component separately. Okay? And why can you do it separately? It's sort of obvious you can switch all the colors, all the red to all the blue. That's not going to cause any problems. But why does it work only in connected components? Well, if you take those graphs, there's no edges between the connected components. So you just think of one connected component as a graph, and you can just switch all the colors there, black, red, and blue. You don't have to worry about the other ones. There's no edges between them, so you're not going to mess up the coloring. A coloring is messed up when there's an edge with the same colors. Okay, so now every planar graph can be colored with 5 colors. Okay, I saw you, the homework, you were tortured by this. Thank you. You're welcome for us making you do that. Sorry. Okay. So this is the same thing. We're doing some inductive proof. We find a degree 5 vertex. We don't know what its color is. We've colored everything else. And then what we do is we look at the connecting component of the blue and the green, and we try to switch the green to blue. If its connecting component is not the same as blue's, that's fine. Blue doesn't switch, right? Because we haven't switched its color. So then we have an extra color to color the middle one, green. Oh, and if that doesn't work, that means the blue and the green are in the same connected component, which means then the orange and the red cannot be, because there would be a crossing. Okay, here okay, there's some graphs. Oh yeah, the complete graph, it's not so interesting. There's a lot of definitions of trees. No, yes, no, that's whether they're a tree or not. Okay, let's go to the end. There's more stuff here, but it's, yeah, okay, whatever. Okay, yeah, the hypercube. Yeah, oh, modular arithmetic. We haven't even done modular arithmetic yet? Oh my. Okay, so yeah. Okay, so the time is going to be about 110 minutes. Some short answers. Get it ideas you learned, right? You see what I want you to get out of this course, right? To be able to look at a statement, argue its correctness, understand why it's correct, right? You should know if you know the material well, this is what's going to happen. You're going to be fast. There's a lot of problems. Let me warn you. You should listen. There's a lot of problems. Don't panic, okay? Or panic. I don't know. Whatever works best for you. Okay, so if you know it well, this is what's going to happen. You're going to be fast. You're going to be correct. It's going to be awesome. If you know a medium, you're not going to be so fast. It's going to be less correct. That's all fine, right? Whatever. You know? Well, that's the problem. Some longer questions, not so many, actually. We kind of manage them so that, just that's the way we do things. Algorithms, properties, not so much calculation. We don't ask you to run algorithms so much in this class. We're trying to get you to think about why they work instead of having you follow recipes. You've done that through K through 12. That's done. Okay? Okay, so, yeah, good studying. Yeah.
About how you derive this formula from Euler's formula to prove whether a graph is planar.
Uh-huh.
Just kind of wrote it down just for reference. I'm just wondering how you arrive at this inequality.